Hello, my name is Ethan Catalanello, and my project investigated the effectiveness of a Lyapunov-based controller for stabilizing an autonomous satellite with onboard robotic manipulators. Unlike ground-based systems, humanity currently has no way of diagnosing or repairing satellites in orbit as a result of their great distance from the Earth. Thus, when these satellites experience anomalies or other issues, they often have to be immediately decommissioned because they can't be repaired. This is a problem because these satellites are often essential to humanity's modern lifestyle, as they are responsible for everyday technologies such as weather prediction, telecommunication, navigation, defense, and even the internet. Additionally, such a practice is very costly for satellite contractors and is completely unsustainable for larger satellite networks. Moreover, it's not in accordance with the accessibility outlined in NASA's Space Technology Mission Directorate, so it really only serves as a temporary solution. To remedy this, DARPA has proposed to create a robotic manipulators to perform diagnostics, maintenance, and other repairs on patient satellites located in geosynchronous orbit. This program aims to greatly extend the working lives of these satellites and pioneer a more robust Earth-based space infrastructure. Unlike robots on Earth, though, such an endeavor is a substantial controls engineering challenge, as there are no fixed structures in space from which the satellite can experience a reaction force. And this makes keeping the satellite steady during operation of the robotic arms very difficult. Let me show you what I mean. Let's say we have a satellite, and the satellite has an onboard robotic arm. When we apply a torque to move the arm, its movement causes the entire system to rotate. In order for DARPA's satellite to be useful, we must design a controller that can keep the satellite fixed regardless of what the arm is doing so that it can effectively perform its function. If hypothetically we exactly knew the torques of the arm on the satellite and the capabilities of the satellite reaction control system, we could effectively cancel the arm torque using either a reaction wheel or thrusters on the satellite. The problem is there's always going to be some error associated with our predictions and measurements. So we need to design a feedback controller that can accept our estimation of what the arm torque, or disturbance, will be, as well as compensate for the small inaccuracies in our model. To do this, I researched utilizing a nonlinear Lyapunov controller to stabilize the satellite's attitude. I first designed a mathematical model of the satellite system to be numerically evaluated in Simulink. The relevant equations for this are shown on the screen now. Once I had the dynamic simulation, I utilized Lyapunov control theory and some additional resources courtesy of the University of Colorado Boulder to create a Lyapunov potential function for the system. Note that a nonlinear controls approach was taken here because of the inherent nonlinearities present in the attitude dynamics equation. This allowed a feedback control law for the system to be developed with gain selected through linearization. Shown here is the block diagram of the system. In order to test its effectiveness, this new Lyapunov controller was compared to a much simpler PID control scheme featuring load estimation developed in a previous research project. This is DARPA's Friend Mark II robotic arm, which they propose will be mounted on the NURSE satellite. In a previous research project, this arm was modeled and simulated in order to extract the disturbance that it would produce on the satellite, given a trajectory. The trajectory shown here is the one utilized in this project to compare the different control schemes. The test satellite's inertia matrix and mass are shown here. These are from a previous research project, and they are based on the limited information provided by DARPA and estimates of the satellite's necessary size and configuration. These animations show the actual, real-time system response to the arm disturbance. While both controllers appear to do a very good job at stabilizing the satellite, the graphs reveal that the Lyapunov controller has less than half of the maximum error that the PID controller has, as well as a much better response time as it returns the satellite to the reference much more quickly. Notice how even after 20 seconds of settling time, the PID controller has still not fully returned the satellite to the reference position. For the previous simulation, we've made a pretty significant assumption that the satellite has both no initial angular velocity and it's pointing at the reference. But in the more general case, this is not valid. In order to truly comprehend the controller's performance, we need to compare them in a hypothetical worst-case scenario where the satellite is randomly rotating, which is called tumbling, and in the presence of a much larger disturbance torque. In this simulation, the satellite was both given an initial angular velocity and subjected to an external disturbance, both of which are shown on screen now. The disturbance was applied for the first 30 seconds, and then the system was given 15 seconds to stabilize. These animations are once again a real-time comparison of the system response for the worst-case scenario tumbling satellite. Notice how the Lyapunov controller very quickly brings the satellite out of the tumble and holds it near perfectly at the reference despite the additional torque. Though it is moving slightly, the amplitude of the applied torque is exceeding 200 Newton meters, which is much more than what would be reasonably expected from the robotic arm. These remarks of good performance unfortunately do not carry to the PID controller, which not only fails to stop the tumble, but actually accelerates the satellite as time goes on, further taking it away from equilibrium. Thus, we conclude that the nonlinear Lyapunov control approach is extremely effective for stabilizing satellites with onboard robotic manipulators. I hope that this project serves to further perpetuate research in autonomous satellite control that will contribute to the development of more Earth-based space infrastructure. Thank you very much for watching.